Greetings to all and welcome to this lecture. We are in module 6, lecture number 4. In this lecture, we will extend our analysis of finding current in terms of charge and surface potential. We will see what is Power-Shah model, and later we will see how we can represent our inversion, which is weak inversion, strong inversion and moderate inversion, in terms of terminal voltages. Meaning we do have a MOSFET. In general, we do have 4 terminals. One is drain, one is source, one is gate and another is body. So we need to represent our inversion, whether we are in weak inversion, moderate inversion or strong inversion, in terms of these terminal voltages. These are the learning outcomes of this lecture, which helps you to understand how to identify the weak, moderate or strong inversion of operation using terminal voltages, because at the end you are actually calculating the drain current in terms of terminal voltages. This lecture will also help you to understand what is the minimum limit of weak inversion, in the sense what is the starting point of the weak inversion we consider when we talk about the MOSFET operation. So let's start our analysis with a quick recap. In our previous analysis, we derived thoroughly how we can derive the current, the drain current equation in terms of surface potential as well as the charge, basically the inversion charge. We started our analysis with our basic model of drift and diffusion, which is nothing but W into minus Q dash into mu into d psi by dx. That's we called it as drift component, and then we said W into mu into phi t q I L dash minus q I 0 dash. That is what we have already derived as a diffusion component. If we talk about the strong inversion, then we have already claimed that drift component dominates, and by further simplification we can get IDS is equals to W divided by L mu into minus qi dash into d psi s with a proper limit. Correct? Then in the previous lectures we have discussed that the linearization of inversion charge or the bulk charge is a very good approach to simplify the model. We considered that qi dash can be approximately linearized as alpha into cox dash into psi s in strong inversion, and hence we can simply replace dqi dash is equals to alpha into cox dash into d psi s, which is nothing but, here you can replace this function of psi s instead of qi. When you do that, you will get IDS is equals to W divided by L, or is equals to W divided by L qi 0 dash to qi L dash into mu into minus qi dash dq. When you integrate it, you will get the equation for drift. So make sure this is IDS 1. We have said that the drift current is directly proportional to the square of inversion charge, and the diffusion current is linearly related with the inversion charge. We moved further and we found that we can represent the drift current and the diffusion current, which is nothing but the total current, as a forward current or the forward saturation and the reverse saturation. Further, we have also said that the better approach to represent our drain current equation in terms of quasi-Fermi potential, meaning if you apply VCB voltage, then I can simply replace my current equation in terms of W divided by L mu into VSB to VDB minus of QI dash into dVCB, where VCB is a voltage which is a function of X. So in our MOSFET we said that this dimension we are taking X, means along the channel, and this dimension we are taking Y from gate to body. So this is body, this is drain, this is source, and this is your gate. Correct? Now we have also said that this Qi is nothing but Qi dash is equals to minus of Cox dash into VGB minus V flat band voltage minus psi s minus QB dash, where psi s is the surface potential and QB is the bulk charge, given as minus of Cox dash gamma root psi s. Keeping all those values in this equation, we can represent the drain current in terms of VCB, which is in 3-terminal MOS a third terminal, which is defined as C. However, when we talk about the MOSFET, we do have two types of VCB. One is at source, so we are calling it as VSB, and one is at drain, we are calling it as VDB. Let's move further to derive a Pao-Shah model. So Pao-Shah model is a model given by the researchers names Pao and Shah. This model will assume that all types of charges are present in the channel, meaning in the previous models we have considered that the inversion layer is nothing but having an infinitesimal small thickness, which is charge sheet approximation. Instead of considering charge sheet approximation, Pao-Shah model considers that in the channel we do have electrons, holes, as well as the ions, which is Na minus Nd or Nd minus Na to be specific, correct. So we will use this model to calculate the overall current flows between drain terminal and source terminal, which is nothing but what? IDS. Let's do some small mathematics to find out what is Pao-Shah model. We'll start our analysis by considering a basic equation of Ey, where Ey is the electric field, is equals to minus of d psi by dy, where psi is the potential in x and y direction, but we are calculating the surface potential or the potential in y direction. So consider this is y direction throughout the course and this is x direction. X means along the channel from 0 to L, and y means from gate to body. So the vertical electric field is can be given by minus d psi by dy, where Ey is nothing but square root of 2 into q divided by epsilon s into signum psi s into square root of p naught phi t e to the power of minus psi y by phi t plus Na minus Nd into psi plus n naught e to the power of minus Vcb divided by phi t into phi t e to the power of psi y by phi t. This equation we have derived in our previous lectures, where we said that in general the electric field can be calculated by Gauss's law, considering all the electrons, the holes and the ions are present in the channel. We derived this equation when we were considering about two-terminal MOS structure. Let's move further and change the variable. So this Ey is not only the function of y along this side, but it is indirectly a function of surface potential or the potential as well along the y. So can I change this y to a psi y, because my electric field is a function of potential also. So I am considering a psi cap as a dummy variable and I am representing this psi y is equals to minus of d psi by dy. So I can change this as dy is equals to d psi by E of psi with a negative sign. Now what is y? In our previous analysis also we have said that let us consider near the surface the y is y surface, and along the depth of the body we consider some point yc where the potential is measured as psi y. So we are measuring the potential at the surface with respect to this point yc. We considered in our analysis that yc is deep in the body where this potential is 0, and with respect to that potential is what? Psi s. when we were solving for inversion charge as well as the electric field, we kept this as our boundary conditions. So here, for the sake of general analysis, we consider that this is Yc and this is Ys. The total potential between this is psi y. So I can rewrite this equation as Yc to Ys is equals to dy is equals to minus of some potential psi y. With respect to this potential is what? Psi s. So d psi by E of psi cap. You can change it as psi cap to have a proper limits of this integration. Now, I know the total charge in the depletion region can be explained as Q times the total charge which is present in this region. So this region is defined between Yc to Ys, and the total charge can be represented by rho of xy, where rho is charge density, dy, right? Rho is charge density, meaning this rho comprises the electron contribution, the hole contribution and the ion contribution, the immobile ions, correct? So we can keep it here and we can find out the inversion charge. For the sake of simplicity, to understand much more depth of Power-Shah model, let us consider again that in the channel we do have only inversion charge, and hence at this stage we are replacing psi y by ny, which is nothing but Na exponential of psi y minus 2 phi f plus Vcb divided by phi t, where you can rewrite this as Na e to the power of minus Vcb divided by phi t into e to the power of psi y minus 2 phi f by phi t. Now you can relate with our previous analysis what we have done in 3-terminal MOS, that the electron contribution is actually captured by Vcb by a factor of e to the power of minus Vcb divided by phi t. Let's go further and see how this integration can be solved. So for the sake of simplicity, we are only considering that inversion charge is present in the channel, and hence Qi dash was be given by Na e to the power of minus Vcb divided by phi t into e to the power of psi y minus 2 phi f by phi t. So the total charge is nothing but what? Q into integration of Yc to Ys. Now here, can I replace this integration with what we have derived earlier as this? So I can represent this equation, the total charge is nothing but Q times integration psi y to psi s Na e to the power of minus Vcb divided by phi t into e to the power of psi y minus 2 phi f divided by phi t d psi as a dummy variable. Now we have seen in our previous lecture that we can derive the current equation as W divided by L mu integration of Vsb to Vdb minus of Qi dash into dVcb. Here there will be a minus term because we are talking about electrons. So this minus and minus become positive. Ultimately you will ended up with IDS is equals to W divided by L mu into double integration. One integration is for surface potential or the potential psi y to psi s, and one with a terminal voltages Vsb to Vdb. Now all factors will come inside the integral because this is a function of Vcb and this is a function of psi s. So you need to write as Na e to the power of psi y minus Vcb plus of 2 phi f divided by phi t into d psi into dVcb, correct? This is the Power-Shah model, which tells us that considering all types of charges, meaning the electrons, the holes and the immobile ions, we can calculate the overall current equation. So yes, this model is much more accurate because it is capturing every charge present in the channel. However, this is computationally inefficient because you need to solve the double integration. That is what over the period of time, we need to have some good amount of approximation to make the model simpler. Now let's move further and see how can we solve further our analysis to represent the drain current in terms of terminal voltage. Instead of playing with the inversion charge, the surface potential, can I not represent my current equation in terms of terminal voltage, which is more important because you are going to implement these devices in the circuits, and in general the circuit designer considered this device as a black box. So if you are considering the device as a black box, then you have the terminal voltage in your hand to play with, and hence this is a prime goal to represent your MOS analysis in terms of terminal voltages. As I mentioned that my MOSFET does have 4 terminals. This terminal I called it as source, this terminal I called it as drain, which is nothing but N plus, this is p-type body, this terminal you can call it as body, and over the oxide you have gate where you are applying Vg. We have discussed thoroughly in previous lectures also that what is the common reference you are taking, that matters a lot. It means suppose if I am taking a reference body, I can simply say I am applying a voltage VDB where body is my reference. However, there is also a possibility I can take source as a reference. So I can apply the voltage between drain to source. That voltage is called VDS. So in next coming lectures, you need to take utmost care which is the reference you are taking care of. That is what we have also considered the body reference model and the source reference model. In this terminal voltage analysis also we will see this kind of analysis where what is the terminal you are keeping as a reference. Let's start our analysis by considering that drain voltage is a bit higher than the source voltage. If you do so, it means what happens, the inversion charge near the drain will be lesser than the inversion charge near the source. I am representing the inversion charge with the dotted lines shows a tapered channel, meaning if you increase VDB, then the inversion charge near the drain will be lesser as compared to near the source. Let us we define this condition as VDB is equals to or greater than VSB. Seeing carefully, you can observe that here I am considering body as a reference. That is what I am representing in terms of VDB. However, if I want to represent in terms of source, then I can rewrite as VDS is equals to VDB minus VSB. So if I want to represent this equation, I can simply represent as VDS greater than equal to 0. So first hand calculation, you can or you have seen that we are generally considering VDS is greater than 0 in NMOS, right? That is what the source as a reference. However, I can represent all those analyses in terms of VDB greater than VSB where I am considering body as a reference. So this simple picture helps you to understand what is the reference point you are opting for. For example, you are taking or representing every terminal voltage with respect to body as a reference, then VMB, a well defined value in our previous lecture, VHB as a onset of moderate inversion and onset of strong inversion, or the maximum point of the weak inversion and the maximum point of the moderate inversion, where VMB is nothing but V flat band voltage plus phi naught plus VSB plus gamma times of phi naught plus VSB. Here you are defining a point with respect to body. But now if I want to represent everything in terms of source as a reference, then I need to do VMB minus VSB, which is nothing but V flat band voltage plus phi naught plus gamma times of phi naught plus VSB. And in our previous lectures, we have defined this term as Vm. That is what is seen here, that if you are considering VGS as a reference or source as a reference, then this axis will be VGS instead of VGB, and this point will be VM. In general, we considered Vm as a threshold value with phi f, phi naught is equals to 2 phi f. Though we have already discussed that this is a bad choice, but in a first hand calculation we can consider Vm as Vt, considering the potential as 2 phi f, where we have already derived this equation as Vt is equals to V flat band voltage plus 2 phi f plus gamma times of 2 phi f plus Vcb, and that is what we have said, that my threshold voltage is a function of Vcb. That is what we have already discussed so far. Here the VHB is nothing but Vm plus Vz. In terms of potential phi naught, we said that this Vz is nothing but 6 times of phi t approximately, which says that there is a sharp demarcation between weak inversion, moderate inversion and strong inversion. I would say there is not a sharp demarcation, but there is a smooth demarcation between weak, moderate and strong inversion. That is what we have defined these values. Let's see how can we find out other limits of weak inversion, because if you remember, we have defined that we do have another limit which is called a lower limit, VLB, which is the onset of weak inversion, below which there will be depletion. After VLB, when the surface potential was phi f, we called it as onset of weak inversion, right? And you remember that VLB can be written as V flat band voltage plus phi f plus Vcb plus gamma times of phi f plus Vcb. Now, why we are not talking much about this VLB? Because when we were talking about the MOS cap, this VLB plays a very important role, which helps us to understand that when you are applying a gate voltage, then how the depletion start, then from depletion to weak inversion, then from weak inversion to moderate and so on. However, when we are talking about the MOSFET or the MOS transistor, then the onset of weak inversion does not play an important role, because nothing is really special in that region. Meaning we just applied the gate voltage, the depletion happens, and then the few amount of inversion charge coming into picture, what we called it as weak inversion. Then the question is how you define what is the onset of weak inversion. In general, MOS analysis or MOSFET analysis, what we do is we plot a current. Let's say we'll discuss from how this graph is coming up. Just take it as granted that this is log of ID and I am plotting with respect to VGS. Then this current is on current, or this current is IDS, the drain to source current. But at some extent it will go below, and when this current is near about 0 voltage, then we call it as leakage current. So when we can simply consider that leakage current is negligible as compared to the main current which is flowing between source and drain, then source and drain, so the arrow will be in this side, in the sense the current will be IDS, drain to source. Then we can say this is the onset of weak inversion or the lower limit of the weak inversion, when the drain current is considered to be much higher than leakage current, or in a vice versa I can say when the leakage current is considered to be negligible in the MOSFET operation, then this is defined as a onset of weak inversion, right? Now, how can I represent my current equation or the analysis what I am representing in terms of terminal voltage with respect to source and drain voltage? To understand this, let's go back and plot a surface potential profile with respect to VCB. This VCB is the voltage of 3 terminal MOS. That's what we have discussed in our previous lecture, that this is VG and this is VCB. Later we said that we are introducing another terminal which is called as drain, and hence at the drain side this VCB is nothing but VDB, and at the source side this is nothing but VSB. So this is at source side and this is at drain side. We have seen that when we increase VCB, the surface potential follows this trend, meaning at the drain end or at the drain end if you increase VDB, or at the source side when you increase VSB, then the surface potential increases and ultimately it will ended up with a maximum surface potential psi SA. This point is defined as onset of weak inversion. So we have defined already these parameters as VQ, VW and VU. We are going to use these parameters in our next lectures also, so that I can help you to understand what is the meaning of Q. So Q means it is a charge dominant region. So in the strong inversion, when you are in strong inversion or from strong to moderate inversion, there is a transition, you defined as VQ. Q stands for charge here. So it is a charge dominant region. Now what is W? W stands for it is an onset of weak inversion. So from moderate to weak, this is the voltage where W stands for weak, and U stands for upper limit of the weak inversion. That's what I said, that when we talk about the MOS transistor, then the upper limit is not generally defined in terms of the analysis what we have showed in two terminal MOS as from here the depletion start, but it depends upon the leakage current value. So let's do the analysis and see what it means. I can define the region of operation in the sense whether my MOSFET is working in strong inversion, weak inversion or moderate inversion, I can see by applying terminal voltages. So let me clear to this. Again I am redrawing the MOS structure as this is source Vs, this is drain Vd and this is gate voltage Vg and this is body voltage. So all the analysis here we are doing considering body as a reference. That is what here I am representing VDB or VSB. Corresponding to VDB and VSB, the surface potentials are psi SL and psi S0 respectively. Consider the case when VDB is greater than or equal to VSB. So when VDB is greater than VSB, what will happen? At the drain side, the surface potential is increases. Beyond a certain point, it will attain a maximum value of psi SA. It means this end is getting depleted or it is weak inverted. However, this side you are not touching VSB. So this is strong inverted. Consider the applied gate voltage in such a way that you are in strong inversion. So initially you applied a gate voltage, so you have a strong inversion like this. Now what happened is you increase VDB, so here the charge concentration is reduced at the drain side and the complete picture will look like this. Is that okay? Now how can I decide that in which region of operation I am working in? In our previous lecture also we decided that the region of operation is defined by seeing the heavily inverted channel present in the MOSFET. Meaning if my source is strongly inverted and drain is weakly inverted, I can say my transistor operates in strong inversion. If my source is working in strong inversion and drain is moderate inversion, I can still say I am in strong inversion. To understand this, let us consider few points in our graph as 5, 4, 3, 2 and 1. Let us consider my source and drain condition, and you can find out in which region of operation you are. So if my source is at 0.5, my drain is at 0.4, the most heavily inverted channel is in strong inversion, which is at the source. So you can say you are in strong inversion. Consider your source is at 0.5 and drain is at 0.3. you are still in strong inversion. Doesn't matter that the drain is at weak inversion or moderate inversion. The same will be good at if the drain will be at 1, you are in strong inversion. Now let us consider your source is at 4 and drain is at 2. The operation will be moderate inversion because your most heavily inverted channel is in moderate inversion. Similarly, if your source is at, let us say, 3 and drain is at 1, you are in weak inversion. Now this is called forward operation, where you are increasing VDB over VSB. This is also true for reverse operation, where you increase VSB over VDB. So the same thing will be true, only the drain will be replaced by source and the source will be replaced by the drain. Meaning, if you increase this voltage, the channel now will look like this. So it will taper like this side, and hence the more heavily inverted region of operation is near the drain, not near the source. So this region of operation or this operation is called a reverse operation. We have also defined these voltages because we are going to use these parameters in our subsequent lectures. So it is very important at this stage that you remember or know how to calculate this VQ and VW. We have derived these equations in 3-terminal MOSFET. We said that VQ is given by minus gamma divided by 2 plus of square root of gamma square by 4 plus VGB minus V flat band voltage minus Vz, where we have discussed that Vz is nothing but approximately 6 times of phi t minus of 2 phi f, and Vw is the onset of weak inversion, which is nothing but minus gamma by 2 plus square root of gamma square by 4 plus VGB minus V flat band voltage whole square. If you see carefully and remember, this is nothing but psi SA, the surface potential which is fixed at depletion and weak inversion and given by a straight line. If you remember that graph, that this is surface potential and it will given like this. So this line was psi SA. Beyond the onset of weak inversion, when you entered in strong inversion, the surface potential get pinned, right, to 2 phi f value, correct. So that's what we have already discussed and derived these formulas. We are going to use this formula to define our region of operation, as I already explained in terms of this graph, mentioning the few points in our graph, that's 1, 2, 3. Let's define in terms of terminal voltages. So I am drawing a graph between VSB and VDB and carefully observe in which region of operation you are. This is very important to model the current equation, because you need to first decide in which region of operation you are actually deriving your current. So this is VDB, this is VSB. Now see, if VDB is less than VQ and VSB is less than VQ, meaning surely you are in strong inversion, correct. You can see from here, if your VDB and VSB is less than VQ, it means both the channel ends are strong inverted. It means you are in strong inversion. Suppose if VDB is increased, then what happens is, here the inversion charge density at the drain end will decrease, but at the source end, if you maintain the voltage which is less than VQ, you are in strong inversion. So you can see simply a strip like this. Whatever be the value of VD is, right, you will be in strong inversion until and unless your VSB will not increase, because this end will be strongly inverted. If you increase VDB in such a way that you go beyond this, the channel will be depleted almost, and hence you will be in strong inversion, but this channel will look like a tapered channel like this, correct. This region of operation is forward operation, where we have already discussed that VDB is greater than VSB, meaning VDS is greater than 0. This will give you a current which is from drain to source is greater than 0 or positive. there is another operation which is called reverse operation. If you just considering a symmetricity of the MOSFET, you increase VSB, keeping VDB either constant or negative direction, you increase or make it negative, right? Then what will happen? You are actually increasing towards this side, keeping this strip as constant. So that region of operation is decided by what is the voltage you are increasing in your MOSFET. Here, if I want to decide what is the minimum limit of the weak inversion, I can simply say this point, because I don't know in terms of voltages. Instead, what we'll do, we'll calculate the current and we'll see when the leakage current is negligible with respect to the drain current, we'll define that this voltage or corresponding to that current, what is the voltage is defined as the minimum limit of the weak inversion. That's what we have already discussed. So in next lectures, we'll derive our region of operations, which is nothing but what? Strong, weak and moderate separately, meaning we will analyze what will happen or what is the current model in strong inversion, in weak inversion and moderate inversion. Why? Because in the region of operation, the different region of operation will give you a different insight, which helps us to understand which is a dominant phenomena in which region of operation. The second thing is, when you operate a device in a particular region, then if you do have a model of that particular region, you will use that model only. So it will definitely reduce the complexity of your whole model. And third, by using this kind of analysis, we can simplify the analysis for the circuit designer, because the ultimate goal is to incorporate this device in the circuits, and hence the circuit designers will happy to use the models frequently in which region of operation they want to operate the circuits. So let me summarize this lecture, that in this region of, so let me summarize this lecture. In this lecture, we said that what is Pao-Shah model, which is a well accurate model but computationally inefficient, because this needs to solve double integration, one with surface potential, so psi y, psi s, and one with VSB to VDB. We have written as e to the power of Na e to the power of psi y minus VCB plus 2 phi f divided by phi t into d psi into dVCB. Then we said that the good idea is to consider the MOSFET as a black box and represent all the current derivation in terms of terminal voltages, which we have as source voltage, drain voltage, body voltage. That is essentially useful because we need to incorporate these devices in the circuits. So we'll stop here for today. Until then, take care.